Hi, my name is Anish. I'm a solutions architect here at Amazon Web Services, specializing in data and analytics, and we're so glad to have you joining us today for the AWS Online Summit. Now, this particular session, Modernize Your Data Warehouse on AWS, is intended to deep dive on Redshift, its architecture and concepts, and the tools that support migrating your data warehouse to AWS. Now, to get things started, let's look at some of the common trends in the world of data warehouses. First, now data is growing at an exponential pace, and this has been the case for years now. With on-premises data warehouses, capacity planning needs to occur well before data growth. Now, once new capacity is purchased, utilization remains low until the data grows. Now, as the data volumes approach capacity, then performance slows down and the users are not happy. Also, traditional data warehouses were not designed or optimized for storing unstructured data such as log files, event data, and others. Now, this poses a big challenge. Next, data exists in silos within your organization, or in cases where it's centralized in an enterprise data warehouse, it's extremely costly to build ETL to move the data. And this type of solution will not scale at petabytes or exabytes data volumes. Now, the pace of business continues to accelerate, and business users want analytics results as soon as possible. The last point here is that people have come to realize that migrating of legacy on-premises data warehouses provides the opportunity for many benefits, such as performance, availability, cost, manageability, and flexibility, and all of this without compromising on security. Now, as products like Netezza reach end of support, we know a lot of customers are interested in taking advantage of the migration tools and programs that AWS and our partners have to offer. Now, with a modern data warehouse, you'll be positioned to take advantage of the exponential growth of data and the benefits of getting end-to-end insights from analyzing all of your data. Now, let's look at how Amazon Redshift addresses some of these challenges and what are the main benefits of modernizing your data warehouse. The first benefit is, with those challenges previously mentioned, adopting a data lake-based architecture for analytics will help you tap into all of your data. You can take advantage of or be ready to evolve into data lake, data sharing, real-time analytics, AI/ML use cases without having to re-architect because Redshift is fully integrated with your data lake. In terms of performance, Redshift is the world's fastest data warehouse with up to 3 times better performance than other cloud data warehouses. And it only keeps getting faster. Continuous performance improvements and optimizations have made Redshift 10 times faster than what it was just a couple of years ago. In terms of value, Redshift delivers 3 things that our customers consistently tell us matter the most when it comes to cost. The first is usage-based pricing instead of license-based pricing. The second is cost savings with reserved instances. And third is a predictable month-to-month spend with no hidden charges and surprises. Now, in terms of scalability, whether you're scaling users or data, Redshift is equipped to help you grow. Now, Redshift clusters scale from 160 gigabytes to 2 petabytes of storage. Resizing is completely managed by AWS, and there's no limit to how often or by how much a cluster can scale. Now, concurrency scaling automatically deploys compute resources when needed to handle thousands of concurrent users and queries. You can also scale to exabytes of data with your Amazon S3 data lake by querying it directly without needing to load it into the data warehouse. In terms of security, AWS has comprehensive security capabilities to satisfy the most demanding requirements, and Amazon Redshift provides better security out of the box at no additional cost. Now, Redshift customers can encrypt data at rest and in transit, also isolate clusters using Amazon VPC, and manage keys using AWS Key Management Service, KMS, and hardware security models. In terms of manageability, Redshift is extremely simple to set up and operate, and most administrative tasks are automated. Now, Redshift has automated backups, is fault-tolerant, and provides flexible querying. Redshift automatically performs maintenance tasks like vacuum and analyze, automatically chooses stable distribution styles, adds cluster as concurrency increases, and optimizes queries by itself. Now, if you're experienced in tuning and administering data warehouse, you also have the option to take more control when you need to, because Redshift provides advanced workload management, query monitoring rules, and detailed monitoring metrics that allow you to tune your specific workload to meet your performance requirements. Now, I'd like to take a couple of minutes to talk about Redshift with data lakes. To realize the value of data and overcome some of the challenges we previously covered, customers are increasingly moving towards data lake architectures. Amazon Redshift provides the ability to live inside your greater data architecture that includes a data lake. This means you get your relatively static business data optimized and stored in the data warehouse with all the benefits of a traditional data warehouse. Benefits such as speed, a system that's easy to set up and use, and the ability to run complex analytic queries against petabytes of structured data. To extend this, Redshift enables customers to directly query and join data across both their Amazon Redshift data warehouse and Amazon S3 data lake, giving customers a lakehouse approach to data warehousing. With Redshift Spectrum, you can query open file formats you already use, such as Avro, CSV, JSON, ORC, Parquet, and more directly in S3. Now, this gives you the flexibility to store highly structured, frequently accessed data in Redshift, as well as keep exabytes of structured and unstructured data in S3 and query seamlessly across both. You also might have a need to get the results from Amazon Redshift queries back into Amazon S3 in an easy way, in an open format that can be used by other services. With the Redshift Data Lake export capability, you can save the results of a query you've run on Redshift into your data lake in Parquet format so that you can analyze that data with other analytics and AI/ML services like SageMaker, Athena, and EMR. To export data to your data lake, you simply use the Redshift unload command in your SQL code and specify Parquet as the file format, and Redshift automatically takes care of data formatting, partitioning, and data movement into S3. Now, this ability to take data from your data lake to the data warehouse and back to the data lake is what we call a lakehouse architecture. Now, as an example, one of our customers, Equinox Fitness, who have a number of health and fitness brands like SoulCycle, recently shifted from Teradata, which was very expensive and was not scaling for them. They moved their data warehouse to Redshift, along with using services such as Redshift Spectrum, EMR, and Athena. And they built the data lake on S3. Now, this has helped them save a lot of money. Their monthly Redshift bill is 20% of yearly maintenance on Teradata. We have tens of thousands of customers who are using Redshift. It is the most broadly used data warehouse in the cloud. Now, these are companies like Electronic Arts and Aetna, McDonald's, Yelp, Dow Jones, Pfizer, Intuit, and Liberty Mutual. And we have more and more customers gravitating to Redshift in significant part because we are continuing to iterate at a much faster pace. So with that background, let's deep dive a bit more to understand the Redshift architecture and the innovations made in the recent times to make Redshift the most compelling data warehouse offering. Let's talk about where Redshift came from. It originated from PostgreSQL, so the SQL syntax in Redshift is very similar to PostgreSQL. But we entirely rewrote the backend to make Redshift into a columnar storage engine. It's also MPP, which means it is deployed in a cluster mode and scale out horizontally. Now, on top of that, we added a lot of OLAP functionality like windowing functions, approximate functions, and a lot of things that you typically use in an analytics database. Now, Amazon Redshift easily integrates with other services in AWS, like, for example, IAM for authentication, S3, which is where you typically load and unload your data. We also have integrations with KMS, which is used to encrypt your data at rest. Now, it is the combination of all these services that makes Redshift a powerful data warehouse for analytics. And we haven't stopped at that. Redshift continues to evolve. We've delivered more than 200 new capabilities in just the last 18 months. Now, I won't be getting into each one of those, but there are a couple that I want to highlight here. The first is on concurrency scaling. Now, this was launched about a year ago. It automatically adds and removes compute capacity based on unpredictable demand. It's incredible how many of our Redshift customers are actually using concurrency scaling. And because we give an hour a day of free usage of concurrency scaling, about 97% of our customers who are using it are actually using it for free. The second feature I want to talk about is we recently released materialized views. Now, materialized views takes your most frequently run queries and pre-computes them and caches the aggregations and the filters and even joins between tables, which makes your queries run much faster. So Redshift is continuing to iterate quickly based on a lot of what you are telling us that matters to you. Now, let's talk a bit more about the architecture. The Redshift architecture is a massively parallel shared nothing columnar architecture. I'm going to start by explaining it at the green box at the top, which is a SQL client or a BI tool. Now, you can connect to Redshift using JDBC, ODBC drivers that are supplied by AWS. Now, you connect to the leader node, the blue box up there. This acts as your query coordinator. In this case, I have 3 compute nodes, but you can have anywhere between 2 and 128 compute nodes. Now, all of your data resides in these compute nodes or in Redshift Managed Storage in case of RA3, and each of these compute nodes execute a query against the data that belongs to it. Now, all of that happens entirely in parallel. The results from each of the compute nodes is sent to the leader node, which returns the data back to whatever client tool that submitted the query. Now, underneath the compute nodes, we have S3. This is typically how you load or unload data. Now, S3 is also used to store automated backups of the data as snapshots. You can launch or restore a new cluster of those snapshots at any point in time. Now, a couple of years ago, we launched Amazon Redshift Spectrum, which is an additional feature of Redshift. Now, Spectrum is an additional layer that sits in between your Redshift compute nodes and the S3 storage. Now, it's a highly scalable layer of compute that gets provisioned at query time. So you can store data in S3 in an open format like Parquet, JSON, or Avro, and you can expose that data in S3 to your Redshift cluster as an external table and query it with the Spectrum layer that is spun up dynamically at query time and executes the query and passes the results into your Redshift cluster. Now, you can even join data in S3 with the data in your cluster so that it makes integration with the data lake much easier. Now, some customers also use it to offload data to reduce cost of storage in their Redshift cluster. Now, with the release of Redshift Managed Storage, we have a combination of SSDs and S3-based storage. Now, Redshift takes care of the movement of data and makes sure the hottest data is in the SSDs, so it effectively allows you to scale an individual compute node to up to 64 terabytes of storage. We also recently introduced Aqua, a new distributed and hardware-accelerated caching layer for Redshift that provides the next phase of performance improvements and innovation for analytics at the new scale of data. Now, Aqua enables Redshift to run up to 10 times faster than any other cloud data warehouse. Aqua for Redshift especially excels at scan and aggregation heavy workloads, where the additional speed will transform the way to analyze large amounts of data. Now, Aqua works with the new Redshift RA3 nodes to provide unparalleled performance. You can now sign up for the Aqua for a Redshift preview to get an advanced look, and Aqua will be generally available in 2020 at no additional cost for Redshift RA3 clusters. Now that we've covered the Redshift architecture, let's understand a bit more in detail on the terminology and concepts so we can make informed decisions while migrating your data warehouse to Redshift. Historically, Amazon Redshift had 2 instance types. The first one was dense compute, or popularly known as DC2, instance types which were backed by solid-state disks, and that provided high performance with a large amount of compute. Whereas dense storage with magnetic disk-backed storage had more storage and lesser compute capacity. So you would pick one of the two depending on what your requirements were. But now, with the new RA3 instances with Redshift Managed Storage, you can provision the amount of compute you need, and we will dynamically in the background provision and manage the amount of storage needed for your cluster. We think RA3 will be the best choice for most customers, particularly with the upcoming release of Aqua, which is included at no extra cost in RA3 nodes. Redshift is a columnar data warehouse, and this helps reduce I/O. The types of queries you typically execute on a data warehouse usually just queries a small subset of the columns in a table. So you might have a table with 200 columns, but you may only query a dozen of the columns at a time. Now, you're going to be doing aggregates across many millions of records. Now, these sort of operations perform better in a columnar architecture as opposed to a row-based database like PostgreSQL. Now, let's understand this with an example. So here, we have a table called Deep Dive with a few sample records. If you want to run this very simple SQL query to find the minimum date in this table, in a row-based database like PostgreSQL, I would have to scan through all the data in that table. However, in Redshift, on the other hand, I can just read through the date column only, as shown here. And I've reduced the amount of I/O done on this particular query. Now, with columnar architecture, Redshift only scans for those blocks of data which has the relevant columns. Now, moving on, let's talk a bit about compression. So using compression is really important in Redshift. It solves two purposes. The first and the most important is that it dramatically reduces the cost of storage for you. You can achieve anywhere between 2 to 4 times compression in Redshift. So this helps you in storing significant more data in your cluster. Now, the second goal is to reduce I/O. We know that for many customers, I/O is still the bottleneck. So we can improve performance by adding compression. Now, compression is usually applied automatically. By default, when you run the copy command, copy automatically analyzes and compresses data on first load into an empty table. You can also use analyze compression, which is a built-in command that will find the optimal compression for each column on an existing table. Now let's look at how that works with an example. Now it's the same table again, without any compression applied to the columns. What you see here is that we changed the DDL statement to apply column encoding, which is essentially compression, and we are shrinking the amount of data that is stored in the underlying storage within Redshift. Now there are 13 different encoding algorithms that you can choose from based on the column's data type. The next concept I want to cover on Redshift is blocks. The key point with blocks is that they're immutable, meaning we never change an existing block. The blocks are the base unit of storage in Redshift and is typically 1 MB in size. They are encoded with one of the 13 different encoding types. A full block can typically store anywhere between a few 100,000 records to millions of records. Now, another concept in Redshift and associated with blocks are zone maps. Now, zone maps essentially are used to eliminate unnecessary I/O. Now, we do this by keeping an in-memory data structure that stores the minimum and the maximum value of every single block we have in the cluster. So Redshift automatically uses that information to reduce the amount of I/O it needs to perform. Now, data sorting makes use of the zone maps to improve the performance of the queries. With sorting and zone maps, you can significantly reduce the number of blocks that are required to be read for a query. Now, in terms of selecting the columns as the sort keys in your table, you can do that by either understanding the query patterns and the common filters used, or you can also decide based on the specific business requirements or the profile of your data. Now, here's an example to understand sorting. We have the same deep dive table. Now, if I were to apply a sort key on this, I'll be changing the table DDL as shown here. This will apply the sorting first by the date and then by the location column. So with the sorting applied, the data will be reorganized in the block storage based on the ordering of the sort column, and this is how it would look like. To tie all these concepts together, which is zone maps and sorting, we can look at this unsorted table. Now, I'm submitting a simple query to count the number of records on a particular day, which is 9th of June. So what Redshift will do is check the zone maps and reduce the I/O on the cluster. It knows it doesn't need to read data out of that one block on disk, but it's still scanning 3 blocks of data. Now, since the data is not sorted, there's an overlap in the min and max values across the different zone maps. Now, if I were to take this exact same table and sort it by the date, you can see the zone maps on the right with the min and max values is now in the sequential order because they were sorted based on the date column. And with sorting, only one block of storage is read based on the date. Now let's understand about slices. Slices are essentially virtual compute nodes that give parallelism within each of the compute nodes in the cluster. Now each compute node is initialized with either 2 or 16 slices depending on the size of the node. The actual data within Redshift is stored on a slice-by-slice basis within the cluster. Now, we can distribute the data to the slices with a few different techniques. The first is distribution style by key. So you assign a particular column in the table to be your distribution key. We look at the value for each row in that column, hash it, and then hash corresponds to one of the slices in the cluster, and that's where the data is stored. Now, distribution style all sends the full table data to the first slice on every node. This is useful when you have small tables, usually dimension tables that you use for a lot of joins. It makes a complete copy of that table on each one of the nodes in the cluster. The next distribution style is even. It is as if you were to say, I don't know what to pick as a distribution style, so please automatically distribute it across the cluster. Now, Redshift uses round robin to distribute the data across all the nodes. Auto combines even and all distribution styles. Redshift will automatically set the table to all, and then when it passes a certain threshold in size, Redshift will convert the table into distribution style even. Now let's look at a few examples to understand the concept of distribution. Now, we have the same deep dive table and the same set of rows, and we have two nodes comprised of two slices each. Now with this style even, the data is going to be evenly distributed across each one of the slices. Now if I were to switch this distribution style by key, by location, this is how the data might get distributed. Now we have SFO, which is going to go to that slice 0, and then we have JFK is going to go back to slice 1, and so on. Now this is an example of bad distribution key, because if I were to execute a query across the cluster, there is no data on node 2, so it's a wasted compute node. Now let's pick a column with high cardinality that could be a primary key, for example. So I'm picking the audience ID instead, and you can see the DDL has been modified. Now with the audience ID, we get perfect distribution with 4 rows across the 4 slices. When you have millions of records, the distribution will work best when you select a high cardinality column, such as the audience ID. Now distribution style all example shows that each record comes into the table is stored on the first slice on each node in the cluster. Now, to summarize the distribution concept in Redshift, and when you pick which type of distribution, distribution style key is primarily used for joins. So if you were writing a SQL statement which joins two large tables, the column that you're joining on would be a good distribution key. For example, if you have orders and order details, if both the tables have an order ID, then that would be a good distribution key to go with. Now, key-based distribution also helps in improving the performance of the insert command, especially when you're loading from one table into another, and both have the same distribution keys. With distribution style all, it's meant for smaller tables, so about 3 million records or less. The generic idea here is to collocate the joins within the same node in the cluster to improve the query performance. Now, distribution style even can be used if you do not know what to pick, and distribution style auto is the new default if you don't define any distribution. Now that we've covered some of the main concepts of Redshift, let's look at what tools are available to accelerate your data warehouse migration into Redshift. First, there is SCT, which is AWS schema conversion tool. Now, with SCT, you can automatically convert the source database schema and the majority of the database objects, including views, stored procedures, and functions, to a format compatible with the target database, which is Redshift here. Now, any objects that cannot be automatically converted are clearly marked so that they can be manually converted to complete the migration. The second service I want to talk about is AWS DMS, which is the database migration service. Now, DMS helps you migrate databases to AWS quickly and securely. The source database remains fully operational during the migration, minimizing downtime to the applications that rely on that particular database. Now, DMS can migrate your data to and from most widely used commercial and open source databases. With DMS, you can continuously replicate your data with high availability and consolidate databases into a petabyte scale data warehouse by streaming data to Amazon Redshift, as well as storing it on Amazon S3. Now, to get started with the migration, you can install SCT, run the tool, and create an assessment report. Now, this gives you an idea of how difficult the migration might be. For example, some databases may have a lot of PL SQL or some sort of stored procedures or binary objects. It will flag all of this, which can be converted and help you plan for the effort required. Now, SCT also can do the one-time movement. You install extractors on an EC2 instance, for example, and they will reach out to your source database after you've converted the schema, and it will move the data across the line into your Redshift cluster. In case you have a lot of data in your source database, the extractors can also drop the data locally. You can order a Snowball Edge and copy the data over into Snowball, send the Snowball up to AWS, and we'll make the data available in S3, and you can continue loading the data into Redshift to complete your migration. Here are some examples of the databases or traditional data warehouses that are supported by the schema conversion tool. To help customers move their database to the cloud, we built the AWS Data Migration Service. DMS helps you move common commercial databases such as Oracle and Microsoft SQL Server open source databases such as MySQL, data warehouses such as Teradata, and even NoSQL databases such as MongoDB to AWS. Now, you can use DMS for one-off migration as well as ongoing replication from the source database to Redshift. So, to summarize, if we are looking to modernize your data warehouse anytime soon, here are a few tips and tricks put together by the specialist teams that have worked with a lot of our customers migrating the data warehouse to Redshift. Now, when moving from legacy row-based data warehouse, it's important to denormalize the data, which might provide performance benefits, especially as Redshift is efficient with wide tables because of the columnar storage and compression. Now, another tip is to avoid date dimension tables to avoid unnecessary joins. Now, when moving from SMP legacy data warehouses, co-location of tables would help with faster joins. So you might want to pay attention to the selection of distribution styles used in your table design. Now, another important point is Redshift is designed for big data. This is amounting to 100 gigabytes to a petabyte scale. Now, if your requirements are to store smaller data sets, then you can consider other alternatives such as Amazon Aurora PostgreSQL. The final point is around leveraging Amazon Redshift stored procedures for faster migrations. Now, support for PL and PGSQL stored procedures were added to make porting legacy procedures easier into Redshift. Now, before we wind up, here are some additional resources that are available to you. There are a few very useful admin scripts and views available in the AWS Lab public Git repo. Now, these scripts are extremely helpful to improve the design of the tables and also identify performance bottlenecks in your Redshift cluster. You can also go through the AWS Big Data blog posts. There are some interesting reads here, such as the Advanced Table Design Playbook and the top 10 performance tuning techniques for Redshift. Now, finally, your team can get started with learning with our free digital training courses, which has over 550 courses, including the 6-hour AWS Cloud Practitioner Essentials course. Now, we offer a variety of learning paths by solution and by role to help advance skills or even prepare your teams for the AWS certification. Plus, we also offer education programs such as AWS Academy and AWS Restart to help you to pursue industry-recognized certifications and in-demand cloud jobs. That brings us to the end of this session. Thank you for attending, and we really appreciate your feedback so that we can better understand the topics and services you'd like to know more about. So please do take the time to fill out our survey and let us know what you think. Thank you again.